pressure, but we'll see how we go. Welcome, everybody. Yes, as Sarah mentioned, I'm Brad. I'm based in Melbourne, and presenting to you the latest release from SCIEX, which is the SCIEX 7500 Plus system. Many of you may already know the 7500 series. Obviously, before that, there's been a number of decades of innovation in triple quad and Q-trap mass spectrometers, and this, of course, is the latest iteration in that line of instruments. I will just get rid of my camera momentarily, and that will allow you to focus more on the presentation than on my face. Okay, so the 7500 Plus system was announced at ASMS this year, with lots of press releases and all that sort of stuff. It is the latest, most sensitive system from SCIEX, and has introduced a number of new features and technology that enable not only this high performance of sensitivity, but also maintaining robustness, so that you've got a longer uptime as well. We're going to go through each of these in some detail, but as an overview, first of all, we have the newly created DJet Plus assembly, which is one of the ion optics components. We will also have something called mass guard technology, which is something which has been in research and development for a number of years at SCIEX, and this is the first instrument that it's been implemented on. The Q0 accelerating electrodes, we will talk a little bit about those and why they're so important to people who are running a lot of concurrent MRM in their method. And finally, a new feature that's been built into the software for the 75 Plus, which is Metrics Tracker. So we'll go through these one by one in the coming slides and talk about some of the benefits that they provide to your lab. So this is the image or a picture of the 7500 Plus ion rail, the ion path. And I guess a couple of things that are worth noting is really the 7500 Plus, the Q1, the Q2, maybe I should pull up my laser pointer. The Q1, the Q2, and the Q3 are really all the same as the 7500. They've got a lot in common with that system. The new DJet assembly sits at the front end, so that analyzes a DJet book. The Q0 has some of that new technology that I spoke.
Brad, sorry to interrupt. I don't know if it's just me, but you're cutting in and out a little bit.
Spoke about. It has the mass guard technology, which is just audio, or it's going to be hard for you to tell me if it's fixed if I don't talk, right? Can we get a thumbs up from anybody in the audience if they think the audio is fine?
It's sounding good now to me.
Okay. That's always the way, isn't it?
We did get some thumbs up.
Get some thumbs up. Excellent. It's always the way, like every Teams meeting ever, it's like you're cutting in and out and the person just stops talking. So all good. Thank you, team. What was I up to? Oh, yes, I was up to the Q0 accelerating electrodes. So the Q0 accelerating electrodes are built onto the back end of Q0 just before we get to Q1, one of those quadrupoles that does a lot of the work. Of course, on this system, like many of our other systems, we have the curved collision cell running into the Q3, which on this system is already built with the Q-trap lenses and Q-trap electrodes built into it. So should you wish to upgrade to the Q-trap functionality at a later date, which would give you enhanced scan modes like MRM cubed, for example, then that can be done through some software upgrades and some engineer tuning. The detector has also been maintained from the 7500 system. So this is a high energy dyno detector, first introduced on the 6500 series systems, and enables us to get extremely good linear dynamic range um, on the system. So up to 6 orders of magnitude um, for most applications. Importantly, for people who already have developed assays on older systems, so anywhere from 4,000, 4,500. There's a lot of commonalities with our series of instruments. So we don't have to retune collision energies and CXPs. And especially going from 65 plus to 7,500, there's no other parameters that require tuning. Declustering potential is removed on the 7,500 series of instruments, both the plus and the predecessor. So that actually simplifies the compound tuning somewhat. So let's take a quick look at the DJet assembly and go into some detail about what it is and its history. So many people on the call may have used or may have been around when it was released, but the API 5000 came out in probably about 2009 or 2007 or something like that. And it was the first system that introduced the QJet ion guide. Before this, we had something called skimmers and focusing lenses, and those components were quite complicated. They required a little bit more of a finicky type of tuning for your compound. With the API 5000, we introduced the QJet ion guide, and it was really leading the way in terms of simplicity of getting your ions into the analyzing region of your mass spec. When the 5500 plus was released, and this was the first of what we call the blue line instruments. This was the first non-beige instrument that we released, and it actually changed the dimensions of the QJet. It became longer, which wasn't to do with sensitivity so much, but some gas dynamics in the front of that particular instrument. And this enabled us to get that same technology that the 5000 had onto that new 5500 platform. So obviously the QJets gave us quite a big sensitivity gain over the older 4000 systems. And then when the 65 plus was released, the QJet underwent a redesign and became a two-stage QJet. This two-stage QJet, again, just to try and capture more of the ions that were produced, gave us another boost over the 5500 series that we could use in our assays. And then 7500 and 7500 plus introduced the dodecapole ion guide, the DJet. Um, and on the 75 plus, it's the DJet plus ion guide. And it consists of, as I said, a DJet back-ended by a QJet, and then that goes into Q0. So we'll have a bit of a closer look at that. So a couple of different angles for you to sort of investigate and have a close look at. But the DJet Plus has this quite unique um, sort of pole design, which starts at a certain thickness and then tapers like a blade down into a point. And this enables us to get to change the radius that we introducing the ions to. So as the ions enter, we've got a lot of gas and a lot of ions to corral, to control. And so they enter the front of the DJet and we essentially squeeze them. I just realized I'm making a lot of hand gestures, which no one can see, but we squeeze them as they travel through the DJet towards the mass analyzer region of the mass spec. And this helps us to control the ions and gets more of those ions to where they need to be. This is another image, the one on the left, the bottom left. You can see looking down the DJet, the arrangement of those poles there. One key thing on the 7500 when we introduced it was that the DJet gave us this really good way of focusing the ions that we were generating, but did require um, some more advanced techniques to clean. So to make sure that we put the uptime back into the hands of our customers, we actually re-engineered the interface of the 75 Plus so that it made it a user cleanable item. So they put a fair bit of work into this, and basically when you get your 75 Plus, you also get a couple of tools to help you remove the the DJet Plus assembly. One thing they give is like a printed tray, which actually has all of the spots for all of the things you're going to need to in the disassembly and the cleaning of the dodecapole. It's pretty cool. I sort of want this for previous instruments now, but it does give you all of the spots so that you can sequentially take this unit apart and then clean it yourself. So quite robust. It only goes back together one way, so you can't actually put it together wrong. And of course, there should be nothing in your tray at the end. It's not like the home projects where you have to have a piece left over. Definitely have to put all the pieces back together. We also have videos that show you how to do that. And of course, either myself or one of our engineers would show you that as part of the initial training. Comes with all the tools, so anything you need is also provided. Okay, so we'll move on now to mass guard technology. So we've given the ability to the users to really take control of when the mass spec is cleaned. And what we wanted to do was also introduce something which gave the users more time between required cleans. So this has been worked on for more than 3 years at the moment. And this is, as I mentioned earlier, the first time we've introduced it onto a commercial system. I'll go quite slowly. If you've got any questions about this after the fact, please let me know. But when we have an analysis, we're normally trying to monitor for MRMs. Now that's probably 95% of the people on this call. We're all about monitoring MRMs. For any particular sample, we have a spectrum of available ions that exist. When we ionize them, they all go into the mass spec. They all travel towards our Q1. Of course, our MRM only requires one of those ions. We don't require a range. Q1 only needs to select a particular ion. So what happens to all of the ions that we're not using in our analysis? Well, as you can imagine, they do land on our electronic components. They do get neutralized, and of course, they stick to surfaces. This is actually one of the leading reasons that systems get contaminated, is ions that are not stable in their trajectory, fly off and hit a quadrupole or a lens and get stuck to those components. So what we've introduced is these T-bar electrodes on Q0, which enable us to set a mass cutoff above our instrument. So all the ions go in, and then the T-bar actually cuts off and absorbs all of those ions that are above our mass of interest. This is important because they're the bits that stick to things and contaminate instruments. Schematically speaking, if we have a look at a quick schematic here, We've got a Q naught, and these T-bars are placed in between the existing quadrupoles. And this actually creates an octopole field element. Now that means that any unstable ions will actually get attracted towards those T-bars, giving us the view there. Now, if we look in the cartoon, we're actually looking down a D-jet. So this isn't a D-jet. They wouldn't let me have one of those. But this is actually a linear accelerator from an older style instrument, but you can actually see the T-bars fit in between the chords on this. And so if we look down the end, that's the view that we're looking at here. So those ions travel down towards the mass spec, and if they're above 100 AMU higher than our target, they will get directed towards those T-bar electrons. So in reality, what does this mean for the end user? Introducing these types of things has to be seamless. We don't want to introduce complicated parameters or complicated equipment. We want it to be as seamless as possible. And this has been achieved by making the adjustment of that cutoff dynamic. So for a given MRM method, this is the MRM table being shown here. No matter what mass is being selected in Q1, the high mass cutoff is automatically adjusted and shifts with the particular Q1 mass you're looking for. Obviously, we chose 100 AMU because we want to make sure that there's no degradation in the amount of the ion you're interested in getting into the system, while still cutting off as many of those high mass ions as we can to help really increase the robustness and maintain performance for longer. So there's no calibration, there's no adjustment, there's no tuning. They're basically either on all the time in your system, and that's how they're used. So in what I think is probably one of the most fun jobs in Toronto, is the researchers who actually get given the task of contaminating instruments on purpose. And this this happens quite a bit with new technology. They really do push these instruments quite hard to make them get contaminated. And this test was no exception. They used a cannabis extract and started just injecting it into a system that didn't have those T-bars on it. And this is actually what you see on the lens. So this lens exists between Q0 before we get into Q1. We actually see this pattern, this silhouette almost of the quadrupole, showing the contamination of that Q0 lens. And that's what we want to try and avoid on our systems. You can also see on the right-hand side an image of the quadrupole. So this is Q1, and you can actually see some staining there on that quadrupole. So that's what happens when you do an accelerated contamination test. You get this kind of staining. The same test performed with the T-bars on, so with a system that has those enabled, gives you a much different picture. So you get far less, almost non-existent staining of those components that are really important in helping to maintain uptime. On the left-hand side is an example of the T-bars themselves. You can actually see the discoloration of that component. And in the next picture up here, that's what one looks like when it's perfectly clean, brand new. And that's what it looks like once it's actually absorbed a lot of those ions that were not needed in Q1. So apart from sort of the prettiness of it, that is a good sign for us because the ions we're not interested in are basically getting redirected somewhere else. So, how did they do a lot of this robustness testing? I think this is kind of an example of one of the tests that was done. So what they did was they basically took a rat plasma extract, and it's probably a little bit more concentrated than you would normally use, and they took away all of the things that you and I might do as part of a normal method. So we might, for example, divert to waste at the beginning of a run, or we might use scheduled ionization to cut off ionization at the beginning and the end. That wasn't done. Very basically doing everything wrong. So introducing dirty samples, lots of matrix, no mitigation, to stop things getting contaminated. And they actually used two dedicated LC systems. One was feeding it a crash plasma mix, so just injecting that crash plasma over and over again. And then every so often, they would actually do an injection of a system suitability. And this just meant that the LC that was doing the really dirty matrix was kept separate from the one that was doing the very nice clean um, system suitability injection. So what did this look like? Well, as you can sort of read there, looking at more than 10,000 matrix injection um, was sort of the point that they got to. And on the left-hand side, we see a couple of different graphs which are quite telling. The 7500 plus sort of continued to maintain its performance beyond that 10,000 injection mark, whereas the 7500, while really sensitive, because of that increased load of material, did contaminate with time. And we lost probably 50% of the signal there due to that heavy contamination that was introduced. So the way this run was set up was that there was a mixture that had three different compounds, and that was injected over and over again. And so we can see here on the right, the repeatability of that give quite good CVs for those analytes. Of course, the plasma was not the only matrix that was used. We've got a lot of people today I see from different industries, including like food and water and that. So I'm sure PFAS and those compounds are of interest to you. But again, looking at avocado, pet food, different food matrices, doing a very similar type of test. This time, just a dedicated LC feeding in the matrix. Again, no diversion, no special tactics to keep things clean. And what we see is this in negative mode now for the PFAS compounds. For the 7500 system, we do see some performance drop off with time. And on the 7500, we're able to maintain high performance for much longer before we start to see a performance degradation occur. So these different, the spice, I should say, I think the spice was Chinese 5-spice or something. It was, if anyone's interested. um, so it's really telling that this is all really due to those T-bar electrodes. This technology has really sort of shown that that approach can really help to maintain uptime for an extended period. Okay, so we've gone through sort of the ease of cleaning the D-jet. We've gone through the fact that perhaps the D-jet, will last a lot longer before you even need to worry about such things. And now I wanted to talk about that other component that we introduced, which was the accelerating electrodes. So same diagram as before. So we're not talking about the T-bars in this one, but we're looking at these accelerating electrodes. So these are additional electrodes, again, placed in between the existing Q0 rod set. And this actually enables us now to increase our MRM acquisition rate to 830 MRMs per second in a non-scheduled um, assay. So, of course, this is sort of um, not something we all would normally do. Normally, we do scheduled MRM, or so we wouldn't have 830 things coming out at the same time. But this is just an illustration of what is possible now because of these improvements in ion optics. So on the right-hand side, this is non-schedule, so 830 MRMs per second with a half a millisecond dwell time and a 0.7 millisecond pause time. And of course, getting really good chromatography, good numbers of points across the peak because of that ultra fast MRM dwell time. In examples where we wanted to sort of see at what level, it's fine to run at extreme levels for slides like that, but in real life, what are you going to be using in the lab? And of course, we're looking at here a food contaminants in multiple different food samples. And now we are using the scheduled MRM algorithm that we have access to through the software. So they set up a number of different tests. So in scheduled MRM, you can adjust the minimum dwell time that you ask for. And so using 2 millisecond dwell, 3 millisecond pause, and importantly, this is all POS-neg switched methods, a 15 millisecond switching time between POS and neg. On this system, on the 75 plus, the minimum switch is actually 5 milliseconds. So of course we tried that as well. 5 milliseconds with a 3 millisecond pause and a 2 millisecond dwell, and kept going down. And the idea here was to get as many of the compounds as possible, achieving the 1 nanogram per mil LOQ. So obviously we wanted good back calculated accuracies down to that level of 1 ppb. At 1 millisecond dwell minimum with 2 millisecond pause and a 5 millisecond settling time, we were able to achieve the majority of compounds at 1 ppb, and then a handful that were either 5 or 10. With those different settings, we're able to still get enough good data points across peaks to enable excellent quantitation. So breaking that experiment down a little bit, obviously there was a lot of MRMs in positive mode, a lot in negative mode, and the breakdown, because of scheduled MRM, a lot of the compounds did have high dwell times, 40 milliseconds, 30 milliseconds, but the majority, just because of the way that they were spread out, the majority of them had very low dwell times, so 2 milliseconds and below. So even with that extreme sort of extremely fast dwell time, we were able to get that performance. And down the bottom, just show a few examples of the chromatography that was achieved and the number of points collected across the peaks. So that's really good for high throughput assays. What I'm looking forward to most when I get my hands on the systems is really method development. So I'm now thinking in my head that I can now run at half millisecond dwell, 0.7 millisecond pause, and do one injection to find all of my retention times without having to break them up. So some of you might have experienced this. You've got 1,000 MRMs and you're trying to get retention times for everything. It can be really hard because you just can't go fast enough to get the the confidence in the data. So with this system, I now know I can push to extremely fast dwell times for 1 or 2 injections, get all my retention times, and then switch into scheduled mode. So that's what I'm looking at getting stuck into. So another application, and I know Tussie here in Melbourne is all over this at the moment. Her and Paul Baker are excited about this one. But for really fast lipid methods, because of the fast scanning times that we're able to do, we can now actually start to get really good resolution across peaks that are eluting very closely together. In this example, we have the 0.5 millisecond dwell, 0.7 millisecond pause, which adds up to 1.2 milliseconds in total to make that measurement, right up to 2.5 millisecond dwell and 2.5 millisecond pause. So when we're running 2.5 and 2.5, the 5 milliseconds, the speed of acquisition means that we can't quite get enough data points across these closely eluting peaks. As we start to do a more rapid cycle time and really push these dwell times lower, we can actually start to resolve those closely eluting species. So pretty happy to sort of experiment with that as well at some point. So these lipid methods, just for a bit of background, I was actually chatting to Tussie this morning about this. These have, they're looking at something like 2,000 MRMs per method to cover a broad range of different lipid species. And that's why they are super excited to get their hands on this type of scan speed. Okay, so again, no point introducing all these fancy mass guards and fancy T-bars and all that stuff if we went backwards at all. And obviously that was a big focus of the team. So a number of examples were generated head to head against the 7500 with the 75 plus. And in this example, it was a therapeutic peptide. So this is liraglutide. It's extracted from rat plasma, and looking at the LLOQ to just make sure that we're not losing anything. And of course, we are able to maintain that really good sensitivity that you would expect. But now, obviously, with some of that additional technology to help you continue to achieve that LLOQ for a long period of time. In terms of broad numbers, a panel of different analytes was also generated. This plot, if you're not familiar with it, is just comparing the distribution of LOQs for a multi-analyte method. And what you want to see is this, which is basically a mirror image showing that the 75 plus is achieving the same performance level in terms of sensitivity as the 75, but with the advantages of having those new components aboard. Okay, so hardware. Talking about that for a bit. We've also introduced some new software features, which I definitely know a number of people I've trained or I've talked to have been asking for, and I think they've delivered quite nicely on that. So we are introducing metrics tracker. So this will be a new piece that fits into your existing SCIEX OS software. It is loaded as a new tile, and there's 2 different options here. The first option, which is on the top half of the screen, is the ability to monitor the tuning of the system. So you can actually, in this example, it's hard to read, but it's positive low mass unit resolution. We're looking at the intensity of Q1 at 10 AMU per second scan speed. So this is the MRM setting. and we can monitor certain masses and see how they perform over time. So if you are tuning the instrument, I don't know how often people generally tune these days, between a month and every 3 months, you might be checking the tuning. We end up with, the ability to look at, am I achieving the same as I was last month? So that's one component. So that's like instrument tune settings. The other component, which is on the bottom of the screen, is the ability for you to load up any data that you've collected over the last however many months or years, really, depending on when you decide to start using it. How this works is that in your everybody who's sitting in front of an instrument now, have a look at your QCs. They usually have a very specific name to them: QCA, QC low, system suitability. There's certain names of standards that we implement. So we can actually look at QCs and standards, and we can actually filter on a certain name. So we can pick QC high or QC low, and we can monitor certain analytes over that time um, to see how our performance is being maintained. So whether that's a whole bunch of PFAS internal standards, maybe it's a THC carboxy that you're monitoring because it's the most critical analyte in your assay. You can keep an eye on that and report on that with time. So this means that you are now in control of, all right, our performance, it has been a few months, um, of running, and now we're starting to see, okay, we're at 90%. All right, well, we'll schedule in a clean for next month, perhaps. So you can book time to make that clean. And hopefully it means that performance changes don't sneak up on you, and you can actually see and monitor what's going on. So that is the last piece of the puzzle, really, in terms of the 7500 plus and the things that it is bringing with it today. So we've got the DJet, again, that ion guide to help capture more of the ions that we produce. The mass guard technology to remove the ions that we don't need for our MRM assays. Q-Naught accelerating electrodes to help us speed up the rate that we can acquire information at, and then metrics tracker to help give you more real-time feedback about the performance and the longevity of your system. So with that, I am open to any and all questions. Many of you who know me, if I don't know the answer, I'll definitely get back to you. You can also email me directly if you have that, or even LinkedIn if you're feeling like contacting me that way. We can have a conversation. But yeah, Sarah, I will throw it back to you.
Excellent. Just put myself back on, and I will just stop the recording.
I think I said 45 minutes, but I've gone